Internet. This is JF, and this is Introduction to Programming in ATS. I'm just gonna go ahead and say now that this is like take 50. So This is probably gonna be a bad video. So what I'll probably do is I'll come back and do it again later. It'll be better later. But just for now, it's gonna be a little bit subpar. I only have myself to work with, so that's how it comes out. Anyway, Chapter 3, Functions. So functions play a foundational role in programming. While it might be possible to program without functions, it wouldn't be you wouldn't want to do that. So ATS provides, it lets you do like for loops and while loops directly. So that would help with programming without functions. But the recommended style is to use functions and to do your loops with recursive functions or tail recursive functions rather than, for loops, rather than something like, let's say you had x plus 2, and you want to parameterize this expression. So rather than take whatever happens to be x at the time of evaluation, you want to have like a bit of code you can reuse to add to any kind of number. So one way to do that is to use a function, but another way to do that is to put it in a file called like x plus 2.hats, and then say local val x equals like 40 and include x plus 2.hats. And there you get it. You get your so when you include this, it would add 40 to 2, and it wouldn't actually do anything because it's not much of an expression. But actually, hold on. Let's actually test this. X plus 2.hats. X plus 2. Then we have this, and I want to say, is there like, can I? This is actually return a value. Syntactic element, line 10. Okay. I'm guessing you can't then. So this local isn't actually an expression, doesn't have a value. So yeah, you'd have to do something like okay. So I changed that from an expression to a valid declaration. Now we'll try x equals 40 and include x plus 2.hats, and we'll have this there. Yeah, that totally works. So there you go. You can add x to arbitrary numbers with sort of knowing. You just have to know what the return value, what the return variable is, and you have to know the parameters. So it's very awkward. It's kind of like a pattern, a design pattern in other languages. So this is a design pattern for this. We can call this the function design pattern. But now, of course, you never do that. You just use a function. So functions is a simple form of abstraction. It says, given an expression, you can, so if you have an exp and it's of type double, which you can multiply this by itself to get square. So square equals that. And if exp is a complex expression, you can bind it. So say, just like you did here. So let's say this is 12 times 12. So you wouldn't want to say 12 times 12 times 12 times 12. It's a lot easier just to give it a name and then say, okay, multiply that thing by itself. Then he uses a let declaration to give an exp a name and then multiply it by itself. But if you were to do this every time you wanted to square something, and then you'd have this code repeated throughout your program. And if you did find a more efficient way of squaring, like he's saying here, then in order to update your program to use the more efficient way of squaring, you have to go through it and find every single time you squared something. And since it doesn't have a name, you just have to recognize this pattern of multiplying something by itself. So you'd find that pattern and then change it to use the new version of square. So yeah, that's lame. And what you'd rather do is make square a function. That way, it's like updating a library that your program depends on. You can get security benefits or performance benefits. So you do the same thing with functions. So the keyword fn initiates the direct definition of a non-recursive function. Yep. So square double x times x. It's got to be a double. And you get 25. All right. In the above example, the function square takes one argument of type x, of the name x, and type double, and returns a value of the type double. And the expression on the expression on the right-hand side of the symbol equal sign is the body of the function, which of course has type double because it says it right here. So these types have to the type of this must be what this says it is. So if you have a more efficient way of doing squaring, we can re-implement it, do what I said before. So if square is just a name, what is the expression it refers to? So if this is just a name and not some kind of magic thing, can it refer to an expression that evaluates to value, where the value is a function? So yeah, you totally can do that. So let's say val square to lam double double. One thing to point out about this is that this is not a closure. This is straight up a function like in C without an environment. Yep, and it's exactly equivalent to that. All right, and if we wish, we can change the name of the function argument. So yeah, instead of x, it could be y. This is called alpha renaming of function arguments. Was there another term earlier? Okay. Okay, yeah. So if I were to change the arguments of this, let's say I had square and then square 2, square 1 and square 2, and the only difference is that the arguments have different names, then these are alpha equivalent. Okay. A lambda expression is a function value. Yeah. So the type of this expression right here is a function, and the type of that function is val square to an extern. Let's do it like this. So extern val square 3 has the type of double to double. And if you were to implement, you probably can't do that. But if you did do square 3, I don't know if you can implement. I don't think you can actually do what I'm trying to do. Like, all right, let's try this. Let's try and do it and see if it makes sense. C double. We're going to have another alpha equivalency here. And make that square 3. Okay, that works. Now let's say this is an int. Like we're going to leave this here, which says it has to be a type double to double, and we're actually going to call it. Actually, hold on. What if I do this? So I don't think it's actually using this extern here. If it were an extern fun, then you could say implement, but no. Okay, so a lambda expression is a function value. I suppose you have a lambda expression representing a binary function. That's a function that takes 2 arguments. So this is an unary function. In order to assign a type to the function, form T1, yeah. You have to verify that the body of the function can be given the type T if the 2 arguments of the function are assumed to have the types T1 and T2. So this is the parts in the previous video where I said, okay, ATS is a programming language. ATS has tuples. It's explaining function arguments right now. So. For instance, the lambda expression, lam x double to x of x. You're going to assign that the function type of double to double. And if you have only one argument, you can simplify that as double to double, like I did earlier. But if you have multiple arguments, or if your single argument has like this symbol, like if it's borrowing a linear value and giving it back, then you have to have parentheses around it. But and normally it's like if you can simplify it, then it'll let you simplify it. All right, so now let's say that we have an exp, a val that's of type, it has a function type. So t1, t2, t. exp doesn't have to be, okay, it's not necessarily a name. It's also not necessarily a lambda expression. So like if I had this val, this exp like randomly within a larger expression, it could be square 2, the name, or it could be lam. So it could be either one, and they're the same thing. And they're saying this is how you do a function call. Okay. If exp is some kind, if exp has the type of a function, regardless of what it is, actually like a name of a function or a lambda expression, then you can call it. And you can give it its arguments of t1 thing, t2 thing, and then it'll give you back a t thing. All right, so let's see an example that builds in the previously defined function square. So we've got square. Let's say that this is now, this alpha equivalent of square 1 is now the square. So the boundary of a ring consists of two circles centered at the same point. So if you have the radiuses are r and r, capital R, lowercase r, then the area of the ring can be computed by the following function. Okay, so we've got a function that uses square to get the area of a ring. So a ring is like, it's two circles, one larger than the other, and you're getting the area of the space between the two circles. Area of ring, double, r double. I really don't like this changing the case thing, but whatever. It's in the same area of badness as like one letter arguments, and it's pretty clear and like a functional language. So it's not like you're going to be like grepping through hundreds of lines for this. Like if this function were long, then you'd give it different names. All right. Let's change what we're printing out. Ring, say 10 and 8. Ring, 10 and 8. All right, it's apparently the area of a ring that's like 10 meters or 8 meters on the inside and 10 meters on the outside is 113 like square meters. Let's see if you can do this. It might say that it might get confused by the binary operator there, but let's see if you can do that. Yeah, you can totally do that. Square R, square R. You don't need parentheses around unary functions. All right, so now the subtraction and the multiplication functions are of type double to double, or they take two doubles and return double, and square is takes a double and returns a double. All right, so function arity. The arity of a function is the number of arguments the function takes. So arity 0, 1, and 2 is nullary, unary, and binary. And then you have 1, 3, which is ternary, and so on. So we have a binary function. Square sum 1 takes an int, another int, and returns an int. So x times x plus y times y. So why are you not reusing this? Square y. Because that's a double. All right. Yeah, we could introduce a symbol and overload square, but let's just not for now. I mean, the same way that this multiply sign is overloaded, or we could do this instead. All right, and then let's print out some more. Whatever, let's just give it two random arguments. So we're getting the sum of squares, so 2 times 2 and 4 times 4, which is 20. And instead of having the binary function square sum 1, we can have an unary function. Sorry, not unary. Unary. An unary function that takes a tuple instead. So xy and 2. So square x plus square y, parentheses. Or let's do it the way with a declaration like it's doing it here. So fun square. Note that this is again it's not a closure. It's not borrowing x from anywhere. Although there's no actual x that could borrow from. But if it would, it's still not doing that. This is a normal function of that environment. All right, and val x and y equal xy. Dynamic identifier w. That expression can be assigned the type int to int. Hold on, line 38. Square sum 2. Oh, I'm not passing it a tuple. I'm passing it just the two arguments. So it said, hey, the square sum, it doesn't have the type that you were telling me. All right, so that works. So this keyword type def introduces the binding between the name int2 and the tuple type int. So we could do without this. Int. Yeah, works the same way. I'm just giving it a name. The function square sum 2 is unary. It only takes one argument, even though that argument has multiple components to it. All right, when applying square sum 2 to a tuple consisting of 1 and -1, we need to write at 1, comma, -1. What? Oh, I see. It's like this. Like this got a type error before. What he's saying is we could have said this instead. That's something I never realized. This looks like application syntax, and like you're saying, oh, I want to apply this to this tuple, which is exactly what it is. It's exactly what you're doing. But it's just a space. It's just syntax to say this is a flat tuple and not like a box tuple. So it's this as opposed to this rather than this as opposed to this. Anyway, I never realized that. I even reread this chapter like a few times before doing the video, and I still didn't notice that point. That's why I'm doing this book, because I miss stuff like this. Okay, so many functional languages, e.g. Haskell and ML, only allow unary functions. Function of multiple arguments is encoded. These languages, the unary function that takes a tuple as its only argument. Well, you can do that, and like SML, I guess, does that sometimes. But normally you don't do that. You use curried functions instead. But that's how you could do it. ATS, however, provides direct support for function of multiple arguments. There's even limited support for variadic functions. And also, in particular, in ATS, curried arguments are not supported very well. Like, you can use them, but there's a performance impact that you might want to be concerned about. All right, so we're going to get to that. We're going to get to arguments, I guess, variadic functions later. I don't remember this book ever getting into them, but maybe we will. All right, we're continuing now. So function interface. So the interface for a function specifies the type assigned to the function. So if you have foo, which is binary and it takes 2 types or returns a third type, then you can write it this way by giving types to each one of the components of the function. So this whole page on the left, it's like something you put in the statics, something you put in a .sats file rather than a .dats file. If you're putting in a .dats file like I am here, then you can still do it. You just have to say extern. So extern foo arg1 t1 arg2 t2. Let's say extern square of sum. So accent private returns an int. But the point of numbering the types is that these could all be different types. It doesn't have to be the same type. Another way we could write this is int. So we have a bunch of examples. So sucint for successor, predint. You're adding ints, you're subtracting and multiplying and dividing them. And they're named with like add int and sub int because the actual overload is just the plus symbol. So you say later, you define all these like add int, and then add what big int, or add ratio, and then you say overload with add int, rather than just defining like a function named plus in like an int module or something. All right, we've got mod and GCD. We've got comparison operators, max and min. Then you can print. You can just take an int and print it to the display, standard output, and also you can take an int and turn it into a string. I don't know if you actually. I'm pretty sure you can. There's like you can do that last thing. So let's do that. String int 2. Yeah, you can totally do that. How about toString? Is that overloaded? It is not overloaded. How about toString as a template? That's not there either. It's probably like toString val or something weird like that. Yeah, toString val. So there's a toString val template that you can use, or you can say toString int, because that is also available. All right, so for now, we're mostly going to use function interfaces for the purpose of presenting functions. I'll show later how the function definition can be separated into 2 parts, a function interface and an implementation that implements the function interface. I kind of mentioned that earlier, but we're going to see it later on. And that the separation is such as pivotal for constructing large programs in a modular style. You put your interface in one file, everybody can load that, and then your implementation is elsewhere. All right, so evaluation of function calls. So this is straightforward. Good. If you have an environment and you take so if we were to evaluate this function call of abs, the absolute value function, given this argument, this expression, and we have some environment that says doesn't tell us anything here. The environment tells us what the definition of abs is. So it's this. It just gives us if x is greater than 0, then x. Otherwise, it gives us the negation of x. So it gives us positive double, whatever kind of double we give it. Okay. So you first evaluate the call to -1. So first thing you do is you say, okay, what's 0 minus 1, -1? And then you say, okay, what's abs? Abs is this thing. And then you apply the value you get to abs, or the other way around. Binding between x. Okay, so saying the environment that you have originally, it includes this x binding. So you have an environment with an x equals -1, which doesn't actually matter here, but if you had like a closure, the closure would include that part of the environment. Then he goes through it, so it's straightforward. So recursive functions. A recursive function can make calls to itself and its body. So it can call not just other functions or other operators like the multiplications we have multiples of. We also call other functions. It can call itself as a function. So it says clearly a non-recursive function is just a special kind of recursive function. It's a recursive function that doesn't actually have any self-calls in it. Okay, that's one way to think about it. which means you can say fun in all cases. So even though above we used fn exclusively, all of these could be fun, and that's totally fine. It doesn't actually change anything. It does change things when you have constraints. If you need it, if you okay, it actually does matter. It actually does matter. In some cases, you'll get like an error that you can fix by taking out this, or by saying the termination metric is you don't actually recur. But for the most part, it doesn't matter. So he considers recursion the most enabling feature a programming language can provide. Yeah. So with recursion, you can do problem solving based on a strategy of reduction. So you take a problem and you separate it into a simpler problem that gets you towards your ultimate solution. And you can't do that without recursion. Yeah. Anyway, it's not the style of how you recursion allows you to solve problems in this style, which is a very good one. All right, and now we're getting into examples. So suppose we want to sum all the integers ranging from 1 to n. So we have, let's say, extern fun sum 1, and we give it an int. It's going to give us back an int. So 1 to n, or this first int, and it's giving us the sum in the second int. Okay, so implement sum 1 n. You don't have to tell it the type of n or the return type because this tells it already. I'm just going to go ahead and do that in advance. If n is greater than or equal to 1, then you can re-recur. Okay, so you see you're wanting to sum from 1 to whatever n is. So let's say n is 10, then you say, okay, well, that's greater than 1. So I'm going to say 10 plus the sum of 9, sum 1 of 9. And then it'll be 10 plus 9 plus 8 plus 7 plus 6 all the way to plus 1. And then once you get to 0, like once this recursive call gets 0, it'll just say, oh yeah, add 0. And it doesn't recur in this case, it just stops. So what this evaluates to, like sum 1 is the same thing as, or sum 1 of like 4. The same of 4 plus 3 plus 2 plus 1 plus 0. And it just builds all these on the stack. So this is not a tail recursive function. To find out the sum of all the integers from 1 to n, we call sum 1 of n. The reduction strategy is straightforward. If it's greater than 1, then we say, okay, take this number that's greater than 1 and add it to the rest of the problem. We can also find, what did I just lost myself. We can also solve the problem by implementing the following recursive function sum2 that sums up all the numbers in a given range. So instead of just assuming 1, we're going to have another one. So sum2. Let's say m and n, and we'll say so from int to int. So if from is less than or equal to, no, hold on. Yeah, see. So if 2 is less than or equal to from, what? N plus 1 n. Okay, so we're adding up. It's the opposite direction of what I expected from the previous example. So let's see if this actually works, because it might not with those variable names. Well, it doesn't especially if I don't use those variable names. Okay, it accepts that, so it's probably fine. So sum of 5 plus 4 plus 3 plus 2 plus 1 is 15 is 0. That doesn't look right. It's from greater than or equal to 2, less than or equal to 2. So you start with like say 1 to 5, and it says, okay, well, if we're still less than, if this is still less than this, then continue and add stuff together, otherwise stop and add 0. So I was doing previously is saying, if the initial condition is the reverse of what you'd expect, then add it, otherwise it's 0. Okay, so now 15, that's good. All right, so this time we call sum2 1 and n in order to find the sum of all the integers ranging from 1 to n. So the reduction strategy, yeah, straightforward. I just explained it. So given integers m and m, there's another strategy for summing up all the integers from m to n. If m does not exceed n, we can find the sum. This is basically, I believe, Euler's, Euler's, or whatever. Yeah, so there's a formula you could use to get the sum of all integers between two ranges arbitrarily, without like actually adding them all together, like in recursive calls or in a loop or otherwise. You just do math, and there it is. So that's great. And this is canonically something that Euler, this guy, found out. I think the story is like in grade school. It's like, hey, here's some busy work, and it's like, well, instead of just doing like multiple like giant times tables or multiple add tables. So, hey, what's 100 plus 99? That's 199. Okay, what about 98? Well, that's so you gotta carry one over, and it gives you like 7, 1. It's like 9 or whatever. So he didn't do that. Like the teacher wanted them to. He said, okay, well, if we're adding up all these numbers from 100 from 1 to 100. So 1, 2, 3, 4, 5. So if we start at the beginning over here, and then start at the end over here, say 100, 99, 98, 97, 96. What you notice is this adds to 101, this adds to 101, this adds to 101. So that's a lot of 101s, and you just do the calculation for that. And that's how that works. So on sum 3, an event, int. Say if m is less than int. If m is less than or equal to n, then what is this? Let's. I'm never going to do let's the way the author wants it to be done. I'm not going to do it. Equals m plus n divided by 2. In sum 3, it's a recursive call. Else 0. Fifteen equals 15 equals 15. Looks good. And he points out that this division is integer division with truncation. All right, so evaluation of recursive function calls. So evaluating a call to a recursive function is the same as evaluating a call to a non-recursive function, pretty much. It says here's Fibonacci. And incidentally, the best way to do this is with a loop. Like a loop is comparable to memoized versions of like this implementation. Anyway, that's a rare case. So suppose we were to evaluate fib2 at a sub-environment n of 0. So this is so it's explaining like how recursive functions work. But again, if you've programmed any language ever with recursive functions, then you're familiar with them. But if you're not familiar with them, then here he explains it very, very clearly using environments and recursive calls. So moving on. Coin changes for fun. All right, so say we have a finite set of positive numbers, and we want to say what is the number of distinct ways for a given integer x to be expressed as the sum of multiples of the positive numbers chosen from S. So give me some positive numbers, just a couple of them, like say 5, 10, 15, or 7, 3, and 6. And all right, I want to tell you like how many ways can you add up those numbers to get to x. So say you have, let's say x is 4, and you have 2 and 3. How many ways can you add up 2 and 3 to get to 4? It's like, well, 2 plus 2, and there you're done. That's it. That's the only way. That's the one way. If we interpret each number in S as a denomination of a coin, you're asking how many ways you can make change. So yeah, if I have a bunch of like some currency, how many ways can I make a particular number of money out of that currency? Out of like infinite amounts of each coin. So if you want to get $1, well, one way is to get 100 pennies, or you can get 4 quarters, or you can get two $half, that kind of thing. And you're just adding up all these different ways of getting $1. So it explains how this works exactly, and then this is the implementation it gets. So I have like a bunch of implementations of this elsewhere that are not actually using this exact method. Whatever, let's do it. So we're typed F for convenience, and we have the coins, 1, 5, 10, 25. And we're saying it's int4, but there's no actual need to say that it's an int4. It clearly is an int4 because it's 4 integers in a tuple, and that's what an int4 is. Alright, set coin get. Event. This said I like this, yeah, I don't like that. Let's change this to an array. Int 4. It doesn't actually demonstrate arrays, specifically because he hasn't even talked about arrays. So we shouldn't really be talking about arrays, but size and array ref. That's not how you do it. I wouldn't do it like that. So this is actually like a heap allocation I'm doing here rather than like a var. Yeah, okay. So we're not using tuples then. From coin get, let's go ahead and still use this. It's fine. It'll get inline probably. If n is greater than or equal to 0. This is a Boolean and, so I'm saying both these are the case. And it's greater than or equal to 0. It's less than 4. And the coins in. And make that an array reference. It doesn't like that. It doesn't like that. There's match of static terms. No, it says can't be resolved except an overload failure. So I can't actually resolve this because it should be an I2 size or something. It should be size T that I'm doing. Okay, what it's actually saying is we can't use unrefined. You can't use primitive types for this. Even though I have like even though I have this kind of code that's like making sure that it fits in the case, it's just not going to accept primitive types with an array reference. So nah, get out of here. This is in fact an int, and this is that make that a primitive type. Int. All right, now this should work. No. Why is it saying I'm applying it to the type of G0 int? Line 70. Okay. Line 70, offset 40. So line 70, offset 40. It's saying this array dereference I'm trying to do. I'm trying to index into the array. And that's bad because it can't be assigned the type G0 int. Why does it want that? So the actual term is void, and the needed term is G0 int. So the needed term, oh, look at this. Look at this right here. So I have if, and I have a conditional, and I say then this, but look at the whole thing. This is an if-then expression, which means what happens if this is a false? Well, if this is false, I don't have an else, so it has to return void in the case of else. So this is mistyped. So, okay. So the coins in that case, else, it's -1 that he wants. There you go. That works. So don't worry, by the time we actually get to arrays, we should be a lot better at this. We're jumping ahead in the book. All right. So void coin change, fun function coin change. It's going to take an int, return an int, and we have a big let expression here with a loop, which I'm just going to call loop. All right, this is clearly not gonna work with my style, so let's go ahead and change this. Zero, then loop, sum and -1. Yeah, I'm not really paying that much attention to this, honestly. But you, of course, should pay incredible amounts of attention to it. Sum is less than 0, then 0, else 1. This is so different from like the implementation I ended up doing elsewhere. In fact, let's go look at that. PS1. Okay. Coin. That's not it. Oh, it's fourth benchmark. So fourth coins. There we go. So yeah, I have all these coins. Coin in Haskell. Coin in fourth. This is what arrays look like in fourth. So you see, it's not ATS doesn't have it that bad with that weird syntax. It could be worse. And coin in ATS. So this is what I went with. So I still have an array. I still went with array, but I'm passing indexes to the array. I'm looping through indexes in order to get all the same kind of stuff. I'm just a big if case, and see if you choose your algorithms around your desire to have giant indentations, then it can look just fine like this. All right. Anyway, back to this. So loop in sum of 3, and see how that works. Special static terms. Oh yeah, because I changed coin get to need refined ints, but it's no longer using that. But there's a cheap way, very cheap way. You can just say, okay, what? Just forget it. G1 of G0. Just make it refined. That works. So let's see if So coins applied to 1,000 is it should be 142,511, which is exactly what it is. So this is implemented correctly. So yeah, that's my code, my modified code, and then you could have used a tuple of 4 ints with a function that turns an int into a lookup into the tuple. But it's not completely just a lookup because you have this this negative case, which is actually used in the loop. So it actually subtracts from itself in some cases where it adds stuff. So that's just weird. Going back to big tabs. All right, tail call and tail recursion. Suppose that a function foo makes a call in its body to a function bar, where foo and bar may be the same function. Okay, if the return value of the call to bar is also the return value of foo, then this call to bar is a tail call. Okay, so you can tail call to yourself, but you can also tail call to other functions. And all it has to be is that the last, if the return value of the function you're calling is your return value, then okay, it's a tail call. Basically, if you're exiting the function after the call, it's a tail call. If foo and bar are the same, then this is a recursive tail call. For example, there are 2 recursive calls in the body of the function f91. But only, okay, so this is a non-tail recursive call, and the outer one is a recursive tail call. And one, so there's an important distinction, like recursive self tail calls versus random tail calls, because the ATS doesn't have it doesn't have general like TCO, like tail call optimization. I'm definitely sure. I'm definitely sure it doesn't. But it does have a recursive tail call optimization. So if you're tail calling if a function is tail calling itself, that's always optimized. If a function is tail calling another function, then it's only optimized in some cases that you can set up, like mutual tail recursion, but in general, you don't get it. And the reason I know you don't get it is because explicitly I remember that, oh yeah, there's a special syntax for mutual recursion. So you need to have a special syntax for mutual recursion, which means you normally don't get tail call optimization. Okay. So if each recursive call in the body of a function is a tail call, the function is a tailed recursive function. Okay, so this is F91 is not tail recursive because it has this one non-tail call. But SumInter is because of all the calls in it, of all the recursive calls, there's only this one that's a tail call. So tail recursive function is often referred to as an iterative function because it can be optimized to a loop. I assume so. It doesn't. Well, I mean, if you've read your structured interpretation of computer programs, if you've read your SICP that you keep by your bedside every night, then you know that there are recursive processes and iterative processes. And tail recursive functions create iterative processes because they don't expand in memory as you get multiple calls. They run fixed memory. So in ATS, the single most important optimization is the one that turns a self-tail call into a local jump, turns into a goto. This optimization effectively turns every tail recursive function into the equivalent of a loop. Although ATS provides direct syntax support for constructing for loops and while loops, just don't do that. Just write a little loop like it did up here. It works fine. This is the case primarily due to the fact that the syntax for writing tail recursive functions is compatible with the syntax for other programming features. So once again, he's not just saying, "Oh, we really like tail recursive calls." Like we did a lot of Erlang and Scheme in the past, and we just really like it. And that's why you should do it. No, there are very important practical reasons to prefer tail recursive calls, but they're still in the future. We'll still get to them. All right. So now I have another example: the 8 queens puzzle. The 8 queens puzzle is a problem of positioning on a chessboard 8 queen pieces where none of them can capture any of the pieces. So this is like a typical like prologue program. So in particular, please note that every recursive function implements this. Yeah, so it's all tail recursive functions used for the implementation of this 8 queens puzzle. Okay. Well. So value of the type int8. Yeah, so 8 ints gives you a tuple of int8. We're defining that type def here. And the reason I'm not doing this is because of print board and the board get. I just don't want to write these functions. And this one especially. Although I'm not going to implement this. You can open the book and implement it yourself if you want, or implement it in other manners. But I'm interested in one particular thing, which is it possible to not repeat yourself so much right here, like still doing it the same way it's doing it? Could you just not do that? Let's like test one. How do we do this? But no. There we go. So local val x equals 1, 2, 3, 4. So I'm pattern matching the T1 to get these values. And I want to do this a bunch of times. So we're adding them all together, and then we're going to go ahead and we're going to subtract them. And for whatever reason, we don't want to like put these all in all the same where, or apply the where to all of them. We're duplicating this for some reason that's important. All right, token is discarded. That doesn't work. Yeah, we can't have expressions here. All right, so adding them all together, you get 10. Multiplying them all together, you get 24. Then subtracting them, you get 8, a negative 8 in order. Okay, so 1, 2, 3, and 4. So now, can I duplicate this pattern match? Okay, it really doesn't like that. Okay, oh, hold on, I didn't do that right. It still really hates that. Okay, what about this? I say val bob equals t1, and bob is actually deconstructing. Whoa, I can do that. Okay, so yeah, instead of having like this giant x0, x1, x2, you could have like a local define or whatever for just this function that says, my big array of variables that I want to bind, or names that I want to give a value to. They're called like bob or whatever. So yeah, so A and B, C and D for all these expressions, they come from these pattern matches. Right, but I couldn't say I couldn't replace the whole expression with Bob. I could replace a value with Bob, and that worked out. All right, moving along. We're not doing the 8 Queens program, but you can. So clearly, so he says, yeah, these functions are awful, but that's because we're using tuples. We could be better, but we haven't explained like arrays yet. He also hasn't explained define yet, so you can't use that either. And it's just kind of since this is Introduction to Programming in ATS, Introduction to Programming and Introduction to ATS, he's doing things in order, so you don't get all the concepts right away. Still, you can do 8 Queens. You can do 8 Queens with just tuples like that. All right, now we're going to do safety test 1 and safety test 2. And he's using the 8 Queen stuff, so I'm still not going to write these. But what are you doing here? Okay, so this is a continuation of 8 Queen stuff. Okay, so safety test 1 is saying, can queens capture each other in one manner, and then the other one is, can queens capture each other in a different manner? And then he does a depth first search algorithm. Right. Basically going through every possible board configuration in a depth first manner and printing out the first one that's a solution, or actually all of the solutions that get printed out. And he mentions the print macro, which we've seen a lot of, so we're not going to talk about that. All right, now mutually recursive functions. So if you have a collection of functions that each have tail calls to each other, normally you wouldn't get tail call optimization. Those would be like normal function calls. However, if we make them mutually recursive in the language, we use a special syntax, then they can be optimized. This is explaining mutual recursion here. He has an example. So I think the classic example is like on is even. Let's do a type def here. So type def an integer test. So int test. And then we're going to have is even. On is even. That's an int test. And we're going to also have an is odd, which is also an int test. So implement is even. So is n 0? If it is 0, then yeah, it's totally is even. 0 is definitely even. Otherwise, is odd of n minus 1. Implement, we do and here. And is odd. So if n is 0, then 0 is definitely not odd, so that's false. Else is even of n minus 1. So this only works for positive numbers, so let's go ahead and just say, well, we'll leave it like that. In the future, in this book, we'll learn how to make this precise and not accept negative numbers or something absurd like that, but we're not going to do that yet. This token is discarded. 108. Okay, so you can't do mutual recursion if you're implementing them, I guess. Okay. So put that aside then. Fun is even, takes an int, returns a bool, and equals this, and that is the same. Yeah, that's fine. All right, so at 42, it's even and it's not odd, and that works with mutual recursion, and hopefully these tail calls and it's goto and it's efficient. If it's not, then regardless of whether it is, we'll be able to tell by looking at the C. Oh, actually, hold on. It's about to tell us in the book itself. So he says, okay, these two definitions are mutually recursive. In fact, it's basically just what I just did. Okay, the mutually recursive tail call to is odd and the body of is even is a tail call, and so on. But if we wanted to be compiled to the local jumps, you can't use this and syntax. You need to say f and x. Okay, now it's, hold on, what's this? What? F and x even and is odd? Okay, so there's line 111, dynamic identifier is odd is unrecognized. 111, 35, 111, right here is odd, but I did it right here. You were happy with it just a moment ago. Why are you no longer happy with it? And it knows it is odd, so it calls it right here, but now down here it no longer likes it. Maybe the book will explain. So it combines into a single call with mutually tail recursive. Okay. It doesn't explain. Huh. Make into. Alright, that doesn't even compile, so I can't do that. Alright, there should be a symbol here, but I don't remember how to do that. I don't remember to look at like the ELF file and do that. Let's look at the C. Is even. So yeah, there is even. This is the actual function. So it returns a bool, takes an int, and has a bunch of temporaries here. Actual fun body. It's not very clear. You can see it. Okay. Tail call up again. Anyway, where is odd? So this is odd. Okay. There isn't is odd. That's weird. So there's a label for is odd. Well, this is a global for it as well. Oh, what I don't see is the function. I don't. So anyway, let's see. If I do this like fun, if I do it without the f and x and without the mutual tail recursion, then it doesn't. It works fine. And if I say f and x to get mutual tail recursion, then it stops working. All right, I'm going to assume for now that this is a bug, and I'll go ahead and report it. So Report me. All right, so yeah, you combine them to a mutually tail recursive function. I think it's an example of a function like this, mool table, that uses two loops. So there's no worries here of the loops, the mutual tail recursion eating one of the values. Like, oh no, I can't call loop 2 anymore because you can at least still call loop 2 and loop 1. That's all you wanted. So like is odd is totally available to is even if I do f and x. So that works fine. But just is odd is no longer available to the remainder of the scope, which is a concern. All right. Yeah, so yeah, you can get a Stack Overflow if you don't have tail calls. All right. In summary, the variability to turn mutually recursive tail calls into local jumps makes it possible to implement embedded loops as mutually tail recursive functions. So you can have like a complex like state machine, it's like jumps between different loops, and it'll be really efficient. It'll work just fine. So yeah, you can have like each state as its own separate loop in your function, loop internal to your function. So yeah, this is indispensable to using recursive functions instead of loops explicitly. All right, now endless functions and closure functions. So endless as a shorthand for environmentalists, which is there's no, the function is by itself. It doesn't have an environment. It doesn't have any free variables. It can't refer to any free variables. They're all either arguments to the function or they're bound within the function. So it's represented by a pointer to some place in the code segment where the object code for executing call function is located. Okay, so it's whatever the language gives you for function pointers or function objects. That's what an endless function is. So if you say int to int, you compile it to C, then you get a normal C int function pointer, or if it is a pointer, if you're passing it around or whatever. So a closure function is also by pointer, but the pointer points to some place where the tuple is located at runtime. So you've got a runtime allocated tuple, which has your environment and also your function. So instead of if you have, say, an int, cloref1 int, so a closure that takes an int and returns an int. And what this is really, when you compile it to C, it's a tuple of an int-to-int function, and then an environment that says, okay, what are your free variables? Oh, well, x equals 42 in this environment. So when in your function, when you say x times, let's say this is like say your parameter is y, then y times x. So you're passing it one int, and that becomes y, and then x you're pulling it from your environment, and that gives you return value. So it's possible that an environment of a closure function is empty, but it's not the same thing as an endless function. So if you use closures and you don't have an environment, it's still different. It's still a different thing. You're just unnecessarily making it less fun for yourself. Well, not necessarily. If you have a high order function, you want to give it an endful function. If a high order function only accepts closures, then you can give it a closure. It'll work fine. Now, this is something that I missed. This right here, like I never ever noticed this when I read this book. So in the following example, let's go ahead and implement this example. We have sum and an event. So we have a function called sum that takes an int and returns an int, and it has a loop. It takes an I event and returns an int. And actually, it has a res event. It's probably like an accumulator, actually. And this function is cloref1 int. All right, let's go ahead and do this again. Oh, I exited, didn't I? Okay, so tab socks to all right. Once again, so you have sum and event and has an internal loop that's a cloref1 with this colon cloref1 syntax. So if I is less than n, less than or equal to n, then loop. Sorry. Okay, so you're counting like up. So you're saying, so they say sum of n, they say n is 5. You start out with like 0 or 1 or whatever. Or 1, obviously. You say, okay, well, if 1 is less than or equal to 5, then add 1 to my accumulator, and then add 1 to the I. So you'll say 1 plus 2 plus 3 plus 4 plus 5, starting with your accumulator. Else return the accumulator. N loop of 1 and 0. Now, there's something really important about this, bro. Hold on. Keyword 115. Oh, I didn't say equals right here. They give the type, but I didn't say that this was the body of the function. This was 100. All right, so if you're adding 1 to 100, it's 5,050, which is correct. And the thing to notice here is like, hey, like this n right here, what is that? How is that there? Like, as I said before, like these internal functions are completely separate. They're environmentless. They're normal functions, just like in C. They don't have any kind of closures things, or they're not closures. But it's certainly acting like a closure because it's acting like this n is in scope, but it can't be in scope without an environment. So how is it in scope? This it goes on to explain. So the inner function loop is a closure function, as indicated by the special syntax : cloref1, and where these angle brackets come from is, let's say you have a function int that returns an int, so int to int, and if you have a closure instead, then it's like an int. If you get an arrow, you say, okay, I want to say this is a closure, so make it a fat arrow, so it's a thicker arrow. And then on the arrowhead, I'm going to write, oh, it's a cloref1. So it's like a thick arrow that you've written closure on, telling you have an int to an int. So this is a version of that. Although the colon, this syntax is used elsewhere. It's not always arrows. So maybe that's not actually the case. So let's see. The inner function is a closure function, as indicated with a special syntax. Okay, the type assigned to loop is denoted by int of int and cloref1 int. So so this loop has the type of a closure. So if I were to say what type is this loop, the type of the loop is int of int, and it's in fact a closure. So it's a cloref, and not just a bare environmentless function, which is what it would be in this case. Saying that's the type of it. Hence, endless functions and closure functions can be distinguished at the level of types. Okay, good. Okay, so let's say if I took out this cloref, you're saying it would actually work? It actually works. So the code could still pass type checking, but its compilation may eventually lead to a warning or even an error indicating the loop cannot be compiled into a top-level function in C. So saying, okay, this is a function, but you're saying it's a function like this. You're saying it's a normal function with this colon here, but you're wrong. It's not a normal function. It's a function that has an environment because it's pulling the n from an environment. So even though this code will be allowed, it's like you're kind of like, come on, yeah, this is actually a closure, isn't it? Be honest. Okay. So the body of the loop contains a variable n that is neither at the top level nor part of the arguments of the loop itself. Okay. So what points out here is that we could just make it an argument. So if we just said like, let's say invent, and then pass n, then it's no longer a closure. You just have n available. And this is how I've been doing it the entire time because I didn't know that the syntax existed. I thought if I did have to use a closure that it would be like a little bit heavier weight, but this actually isn't heavy weight. So as it goes on to explain. Yeah, so again, you can go and with a simple transformation, you can make in a closure like this, a closure function like this, into an environmentless function. As a matter of fact, what happens during compilation is the first implementation of sum and loop get translated more or less into the second implementation. There is no actual creation of closures at runtime. So this thing I just did within making that part of the parameters, that's what happens at compile time. That's what ATS does. So it turns this into this. So if I have a cloref1 like as an internal loop, and all it does is refer to variables that are part of the the environment of the function it's already in. Like it's not a real closure. It's just it's a closure that we know everything about, and it doesn't actually have any free variables. Ultimately, I guess you could say. Then it gets compiled into those free variables get compiled into arguments, and it's totally fine. There's no actual creation of closures at runtime, so there's no memory cost to that. You're not allocating anything. It's fine. It's as efficient as you can get with functions. So the need for creating closures often appears when a function is not directly applied. So here we're defining loop, and then we're immediately applying loop. So we know everything about loop, we know everything about its code paths and what variables it refers to and where they are and so on. But let's say instead of just calling loop and discarding it, I would say, okay, let's call like a higher order function, like higher order, we're passing it loop and then our in. In this case, it definitely has to be a closure and it won't have benefit from this optimization. Make sure that's still right. All right. All right, so this is different. We have an ATX. So we have a closure producer. We have a fun called ATX. And give it an X, and it returns you a function. This type does this type here. This whole type is a type of the return value of the function. So it gets an int, so its parameter is type of int, and its return type is this cloref, this closure that takes an int and returns an int itself. All right. Oh, hold on. Well, I guess I'll just stick with this from now on for a while. No, I won't. I definitely won't. Okay, so lambda y is x plus y. So if you run this, it returns a lambda that has an environment. In this case, it has to allocate memory. So it has to allocate memory to preserve this lambda, so you can call it multiple times as you want and have this x as part of its environment. So add 5 to 100, that gives you 105. And the cost of the creating the lambda is paid here. It's not paid here. So even if I call this 1,000 times, it's not going to allocate a memory for 1,000 environments. Like that's already done. So it should be clear that plus 1 and plus 2 return 1 and 2 respectively. So these are adders like I just created. And the closure function is given the name plus 1 consists of an endless function and of an environment binding of x to 1. So add 5 is secretly an int to int with an x or a y equals 5 environment. Notice that this isn't real syntax. This is just imaginary tuple syntax. So the endless function can be pseudo syntax. Okay, so describing the endless function, again, another way to do it is to say that it is a lam of environment in y that returns environment of x plus y. So let's say this were a record, and the record has all the values as record keys. So you can say, okay, well, end of x plus y. There you go. That's how it works. In fact, that's literally how it works. So add x fake. Let's say fake x. Well, if returning a function, we can't actually cheat that much. Never mind. But yeah, you could totally create a lambda and pass it an environment as an argument. I'm getting a little bit tired here. Closures are often passed as arguments to functions that are referred to as high-order functions, and that is what we're going to go into. We're so close to the end. I'm going to continue. All right. So high-order functions. So high-order functions are functions that take functions as arguments. So we have rtfind, which takes a function, takes an int and returns an int, and it looks for f of n equals 0. Yeah. What a weird function. So its only argument is a function, and it returns whatever But how do you loop? What do you loop? Okay, n plus 1. Okay, I get it. So find takes a function, so int to int. Doesn't need an environment. Rather, it doesn't allow an environment because a closure would have a different type. So you might want to have a closure pass to this, but you couldn't do it. You'd have to have like a separate RT-find for that. Anyway, let's not do this. Let's say it's implemented as loop of f is 0, where fun loop. Let's make this a closure function. So fun loop actually takes n instead, and it's a clear f1 and returns int. So I think that's right, yeah. So if f of n equals 0, then n, else continue. Just n plus 1. So I don't have to do that then. So we start out with 0 and we just count up. So 0, 1, 2, 3, 4, 5, and we keep trying until we get the number that RT-find, or the number where this fun returns 0. So I'll just create it and say like, oh, and we'll say RT-find of k, where fun k just takes an int and returns an int. And if n equals 5, then 0, else n plus 1. So it starts with 0, so that'll give it, so it'll return 1, 2, 3, 4, 0, and then it should stop. And then this should print out RT-find equals 5. And instead of a giant error, so I want to say, what did I do here? So the actual term is some kind of var, and the needed term is some kind of refined int that's related to some other variable. Okay, we'll just go to the line number, 134. Okay, right here. So I'm returning an int. Wow. Oh, hold on, I didn't give this a type. That's probably a problem. Yes, that was in fact the problem. Okay, so RT-find returns 5 as expected because 5 is the number where this function right here that I'm passing to it returns 0. For every other number, it returns n plus 1. So if it started with like -1, then that would also work. RT5 equals -1. All right, so this is the same thing, the same exact code as over here. Just I prefer to do it as a function closure because I think it looks nicer. Like that's how you do it in other languages. Like I just never knew that this existed and that it was the same thing, just passing the args manually. Because think about it, like you have to. It's not like troublesome to pass args manually, but like you've got to repeat the type, and look how long this is. So again, if you code around having giant indentations, then it encourages you to be a little bit neater, don't you think? Let's continue. So given a function from integers to integers, RT-find searches for the first natural number that is the root of the function. So in our quadratic equation where it returns 0. Okay. Polynomial function. So let's give it like an actual quadratic equation. RT-find of quad. So x times x minus x minus 100. Okay, that's not what I would expect. So x times x minus 100. Yeah. Okay, maybe I'm insane, but I don't think so. Lamb of x times x minus 110. Oh, I did. Okay, that's probably actually the reason. Okay, 11. Okay, 11 as expected. And there's with this other value that I did, there's a very different answer that's way off. All right, so higher order functions greatly facilitate code reuse. And we give an example of one, sum and prod. Okay, so sum and prod are very, very similar. Like you're doing the sum of integers up to n and the prod of integers up to n. So this is if you do 5, then it's 5 times 4 times 3 times 2 times 1. If you do prod, then this is 5 plus 4 plus 3 plus 2 plus 1. So it would be nice if you didn't have to do that, if you had like a fold function, of course. So this is what he defines a higher order I fold, so int fold. So you give it a range of integers, and it does a fold across that range without having to have like an actual data structure. So I fold, so an event, and then f, which is int to int. Then you have your accumulator, we call ACK instead of in the int. And let's say case n of, if it's a 0, then you return f of I fold, n minus 1, f and ACK, and then that is totally wrong. All right, so now fun can be defined, and sum and prod can be defined in terms of these. So I fold. It doesn't matter that we have sum above. We've already defined sum, but we'll just overwrite it over here. So some of like 5. Let's say an I fold of 5, lam of ACK and x. All right, now let's print these out. Sum of 5 from 1 plus 2 plus 3 plus 4 plus 5 is 15, and then the factorial of 5 is 120. All right, so if you ever want to compute the sum of the squares of the integers, then you can do that the same exact way, just create a different one. So let's see, val, hold on. Sum square. Let's say val sum square. Of n, I fold n of ACK and x plus x times 2, x times x rather, and 0. Yeah. The sum of squares from 1, 2, 3, 4, 5 is 55. So 25 plus 16 plus da da da. All right. I'm going to generalize it. Well, if you want to generalize sum of squares, so the following function, in order to compute the sum of squares of the integers ranging from n to n that are multiples of a given number d. Okay, so not all integers, but just those integers that pass a test. So I guess that's okay. So basically what I did, but if x mod d equals 0, so if if d is a factor of x, then go ahead and do this. Otherwise, just return your accumulator and don't do anything to it. All right. So someone unfamiliar with the distinction between an endless function and a closure function, maybe it's surprising to learn this generalization does not actually work. The simple reason is that ifold expects its second argument to be an endless function, but hold on, yeah, that's the point. He's saying that this doesn't actually work. This code right here, that I said, oh yeah, that's what it does. It doesn't work. This is what I explained earlier, that this lam right here is actually a closure. So yeah, the d here. The d here is a variable coming from square mod sum. So earlier when we did like this loop in chlorf1, this is fine because we created it, we applied it directly, and it's not actually, we never actually had to create a closure for it. But here, since the actual application of the function happens in ifold, not in square mod sum, then you do have to create a function and pass it to ifold, and ifold runs it, and then it needs an environment to get the d out of, and so on. All right. So to address this issue, we implement a variant of ifold that allows us to use that. And this variant is just the exact same function we had before, except instead of taking an endless function, it takes a closure. This is a different type. While ifold2 is indeed more general than ifold, the original one, the generality comes with a price. Because whenever you call square mod sum, you got to create the closure, and you create it on the heap, and then you pass the closure to ifold2. So every single time you call square mod sum, you're creating a closure. That's kind of painful. This closure function is of no use after the call returns, and the memory it occupies can only be properly reclaimed through garbage collection. So if you do that, you need garbage collection. However, you can create a different type of linear closure functions which don't cause memory leaks even in the absence of a GC, as they're explicitly freed. So yeah. So if you want to do it like this, you need to have a GC, but there is an alternative, and we will see that later on. All right, now we have an example of binary searching. So while binary search is often performed on an ordered array to check if the given element is stored in that array, you can also do it with an increasing or a decreasing function on integers. So you can apply it rather than on an array, you can apply it on a function. So in the following code, the defined function bsearchFun returns an integer 10 such that f of I is less than or equal to x of 0, such that that holds for I ranging from lower bound to I0 inclusive. And x is less than f of I holds for I ranging from I0 plus 1 to upper bound inclusive. Okay, whatever. So where do you actually use this? For an integer square root? So the following function, integer square, is defined based on bsearchFun. So use a binary search to implement an integer square root. Using this function, it takes I and gives you the square of I. This right here, the G0 ITU, it's just taking I and turning it into an unsigned number. Pretty sure. Oh yeah. So unsigned, and then this is uint. Okay, yeah. So bsearchFun is passing in like actual ints, and you want to make sure that int is a uint in this function before you square it. All right, so you can do that if you want. I'm not going to do that. That's pretty interesting though. Net the function, casting a signed integer to an unsigned one, and the function returns the square of its argument. Oh, the function square returns the square of its argument. I was like, wait, square root returns a square? That doesn't seem right. All right, now we have a high order fun puzzle. So we have a type def I, which is defined on a type, takes an A. So it's so type def I of A is a closure that takes an A and returns an A. Cloref1. So if I had like an I of int, then that would be an int to int. All right. So given the type t, it is a closure function that maps the given input value of type t to the output value of the same type t. Given a function f of type I of t, we can compose f with itself to form another function that applies f twice to the given argument. Okay, so f of t of whatever x, whatever argument isn't actually stated there. So the following function template twice does precisely the described function composition. Okay. So this is a template twice. Takes an f of I of a. This is a nice abbreviation for just some kind of closure that takes a and returns a. All right, and as a cloref, it returns a cloref of I of a. So it returns a closure that takes an a and returns an a. And it's implemented as lemma of x equals f of x. Keyword, what is it? Line 158. What? Line 158, offset 14, the keyword quote close parenthesis is needed. Close parenthesis is needed. Oh no, I don't see it actually. $58. The keyword equals is needed. So type def I of a of easy to get a typo when it's something weird like that. It's 160, and then he's saying now that something's wrong at offset 28 twice. Is it possible that this is a typo? No. So line 160, 28 over. FU. Well, that's rather rude of you, myself. Termination metric is missing. Okay, so this is where it's needed. Like, I don't know why it needs it here, but it needs to know that this is not a recursive function. So one way to say it's not a recursive function is to say, delete that, now it's non-recursive, and that'll be fine. Yep. Another way is to leave the FU, or you leave the U in the fun, and then to give it a termination metric of like nothing. That accepts that as well. So there are two ways to say that it's non-recursive. And then I don't actually know why you need that. Maybe it's a template. So take a look at the following interesting code involving twice. Is likely to be puzzling. So there's something weird about this code. So I0 is int, I1 is I of int. It's a function that takes an int and returns an int. I2 takes a function that takes int and returns an int, and then returns a function that takes int and returns an int. And I of 3 is you get another abstraction. So we're down to like a function that takes an int and returns an int, and takes an int that takes an int and returns that, or whatever. Okay, so val z equals 0, and val s equals a lambda and x. It adds 1 to x. But you haven't explained what this equal cloref sign is. So I don't actually know what that is. It's some kind of closure anyway. So, okay, so, but where does it say it's returning a closure? Anyway, let's implement this and see what's going on. So type def io0 is int. We're doing this stuff over it. 2 I have 3, or 2 I have 1. Then we have val z equals 0, val s equals lam of x. We're giving them types for some reason. Cloref equals 1. And then we have 4 answers. So twice I have 0, s, and z. I'm doing twice multiple times, so twice of I1 outside that. But it's not S of Z, okay? That's twice of I1. Twice of, okay, I get it. Sure, everything is properly parenthesized. Okay, so that accepts that. Let's print out the answers if you can. It's actually, well, the type has to be int, doesn't it? Ends 3 is unrecognized. In some languages, like this is an error, but it's not the case here. Well, you get bit anyway. So 2, 4, 16, and 16 bits all set to 1. So it said 0, we're applying suck to 0, so we get 1. Doing that twice, we get 2. And then doing that twice, we get 4. And then so you get powers of 2. So it goes from this. So this is 2 to 1, 2 to 2, 2 to what? No, 2 to 1, 2 to 2, 2 to 4, and then 2 to 16. Wow. Okay. Okay, I'll leave these questions as exercises to the answered reader. So if you're interested in why we get 2 to 1, 2 to 2, 2 to 4, 2 to 16 out of this stuff, then go ahead and go ahead and check it out yourself. All right, currying and uncurrying. So currying, which is named after somebody, means to turn a function taking multiple arguments simultaneously into a function of the same body that takes these arguments sequentially. Uncurrying means precisely the opposite of currying. So taking the option. If you're taking multiple arguments sequentially, how about you just take them all at once? So in the following code, both of these functions, ACR1 and ACR2, implement ACR's function, which is it's recursive but not primitive recursive. So there's multiple recursions. Oh yeah, look at that. And okay, so look at this. So this is normal ATS that we've seen it so far. This is a function, it's recursive, okay? And this is a function, okay, you've got this call here and this call here. So are these two separate parameter lists? Yes, they are. So these are your first parameter, and then your second parameter, and then in order to call it, you have to give it parameters in order. So this is the first parameter, and this is the second parameter. And over here, this is your first parameter, and this is your second parameter. And these are applied to curried functions. So you can call ACR, you can call it with n-1 by itself, and you'll get a function back that you can then apply to other stuff if you want. So I'm not going to do this. So the function ACR2 is a curried function of ACR, a curried version of ACR1, while the and vice versa. So yeah, the first one is uncurried version of ACR2. So applying ACR2 to an integer value generates a closure function, which causes a memory leak unless you have a GC. So, in ML and Haskell, like curried functions are the norm, but in ATS, don't use them. Use uncurried functions. Yeah. So a curried function is generally going to perform less efficiently at runtime than the function itself, due to how ATS does curried functions right now. So yeah, don't do them, and if you do them, then you're going to be punished by performance. So just don't. Right. You can though, and just definitely don't do it in recursively like this because this will really hurt. But if you have like a general like higher order function, you want to have like you want to get at like multiple curried versions of it. One way is just to implement it as a curried function, and then like assign your intermediates. So let's say for a really silly example, fun of test takes an int and takes another int and returns an int. Takes another int, give it a different name. Okay. So n plus m, that's what it does. So test 5 equals test of 5. And then you can do like that. Basically add 5 from earlier. Keyword equal sign is needed at 183. Well, yeah, it certainly is needed. It's a very good error message, thank you. Test 5 of 10 equals 15. So one thing I'd like to point out here is that we've got our curried function down here, test. Let's go find that other function that we did. So add 5. Yeah, so we got this versus this. Isn't this neater? Like, there's a price you pay for it, and the price is if you forget that this is a curried function and call like test5 10 in a loop, then it'll really hurt because you'll be creating, and actually you can't do this. You have to do like this. So you really can't forget it. Just know that curried functions are super expensive, and you shouldn't call them in a tight loop like this because you'll create intermediates and then they'll have to be garbage collected. But if you're using it just kind of like an add five, like okay, just I want to get the curried version of this and save that and then call that a bunch of times, then you don't pay the price every time. That's cheaper. However, one thing you can't do with the syntax is use the linear closures that are going to come up later. So if you want to be more efficient, you can do this. But if you want to be neater and use a GC, then you can do it this way instead. All right, that's a long chapter, and again, for many reasons, I feel like it's probably not going to be a very good chapter, so I might go around and do it again later. But for now, that was functions from Introduction to Programming in ATS, and the next chapter is going to be a really awesome one, getting to ML-style data types. For now, that is all.